I'm going to demonstrate an example of using Kirchoffs laws to solve a somewhat complex circuit problem. I've chosen from the 7th edition of Halliday, Resnick, and Walker, problem number 27. And that one, because of the numbers they give, could actually be done with some shortcuts. But for the beginner, I don't know that shortcuts are necessarily the way to go. One of the things that simplifies this problem is that 4 out of the 5 resistors that are shown in the figure are all the same. So we could reduce this down very nicely, especially with the numbers that they give. But what I'm going to do is just basically use the figure and the symbols that they give without putting any numbers in, and show you how we go about getting the correct number of independent equations to find the current in each of the branches. And that is typically the kind of question that's asked about this. How much current goes through each part of the circuit? And then sometimes we follow up with questions like, well, if we know the current, then how much power is being dissipated in a resistor? Or how much energy is being dissipated? The power is the rate at which that happens. Or how much power is being developed at the EMF device. Those are other questions that are asked. But for now, just setting up the correct number of equations and how that's done. We use what's known as Kirchoffs junction rule and Kirchoffs loop rule. Now these are actually rules that we've described in different ways. The junction rule simply says that where wires meet, and in this figure there are 2 places, we labeled them A and B just for reference. Where wires meet, we can't create new current, we can't get rid of the current, and so any current going into a junction has to equal the current coming out, much like cars entering and exiting an intersection. You can't create new cars in the middle of the intersection, nor can you get rid of ones in the intersection. So in this particular problem, we have 2 junctions. So I think what might be good now is to actually label how many different currents we have in this. And that's if you just trace around the figure with your finger and you say, well, how many different places can we change the current? Well, that only happens at a junction. And so I'm going to label with green here all of the different currents in the different branches. I would have what I call sort of the center branch and then the left and the right branch. And you totally randomly choose directions for these currents. Now, they may not match the actual direction that the current ends up going, but for this particular process, you don't need to know that in advance. And so I'm just going to, just for convenience sake, have all of my currents running towards that junction that we call A. So picture current, I'll just draw it around the outside here, that's going through that branch, and we need to draw an arrow showing which way it's going and label it. I'm going to call this I1. We usually just label them with subscripts showing the different numbers of currents. And then we have current going through the right-hand branch. I'm going to call that I3, and I'll just again randomly choose to have it going towards that junction called A. And then we're going to have current in the center branch. I'm going to draw that upward on this figure, and I'll call that I2. I'm just labeling 1, 2, and 3 sort of geographically from left to right. So all of the current going in and out of those junctions has to be the same. The other rule is called the loop rule. And that means as you go from one spot on the circuit, again, maybe we start at the position we called A. If you go in a complete round trip, taking whatever path you wish, you cannot change the potential or the voltage in the process of going around that loop. So in a complete loop, the difference in the voltage, any jumps or drops in voltage, has to equal 0. Now, what's responsible for jumps and drops are things that are in the circuit. Excuse me, for example, you could have a battery that's boosting or dropping the voltage. You could have resistors that's dropping the voltage. You could also, in different circuits, have capacitors and other devices as well. But we're going to restrict ourselves here to what we call EMF devices, things like batteries. and resistors. Those are just kind of generic resistors that we've got in this figure. So the other thing we have to do, and this is again an arbitrary choice, and I'm going to label them in blue, we have to decide which loops we would like to use to generate our equations. I'm going to choose, in this case, the left loop, and that again, I'm just imagining if I start at point A and I circle around to point A, how I go about getting there. I could go clockwise or counterclockwise. I'm going to show with the blue here that I'm going to make a clockwise trip around loop L. I'm calling it L because it's on the left side of the figure. And then I'm going to make also a clockwise loop here on the right side, and I will call that loop R because it's on the right side of the figure. A third alternative, although I don't need a third alternative here, is to draw a loop around the entire perimeter and just avoid that middle branch. Now, if I did that loop, I would just find it's redundant with the other two put together. So in this case, I have three different currents in the entire circuit, and so I need three independent equations, because in algebra you learned that you need three equations to solve for three unknowns. So now I'm going to go through the process of writing those equations. We're going to choose one of our junctions and write an equation basically showing that all of the current going in there has to be balanced out by the current coming out. Now you look at this figure and say, well, you have a problem here because you have all the currents going in. That can't physically happen. But I'll remind you that what we actually did was we randomly chose the direction for the current. Okay, I'm sorry, I got sidetracked there a little bit. So it was a random choice which way we drew the currents. So we know that at least one of those is wrong. There has to be some current going in and some going out. But again, that does not matter. What I'm going to do is I'm going to write an equation. I'm going to label this J sub A. That's the junction equation at junction called A. And all I have to do is show that the total current in, which is I1 plus I2 plus I3, has to equal the total current that I have coming out, which is 0. Now I'm going to write two independent loop equations, and I've already labeled the loops. So the two parts, or the two terms that you end up writing for these equations are the voltage jumps or drops that you get across batteries. EMF devices is another name for that, or resistors. And what you have to do is look at the direction that you've chosen for your loop, a random choice, and the direction that you chose for your current. And if you go through a resistor, across a resistor, in a direction that's opposite what you chose for your current, then you write a plus IR. You remember that the voltage difference across a resistor is I times R. That's if you're going in the direction of the current. That's when it's a drop. So because we're going opposite, then we would write it as a positive IR. If you go across a battery in the direction of the EMF arrow, and these are shown here in red, then it's a positive E. And if you go opposite that, then you write it as a negative E. It makes much more sense when you actually do it. So I'm going to start at point A, just for it's a convenient reference. So this is going to be the left loop starting at A. So I'll call it a loop equation on the left starting at A. Not really an equal sign there. And I'm going to take into account all of the jumps and drops in voltage. So I'm going to actually start heading down that center branch, and I go across resistor number 2 in the opposite direction to how I arbitrarily chose the current, called I2. So because that's opposite, I write a positive I2 times R2. And then I get to the EMF device known as E2. Notice my random choice for my loop is opposite the EMF arrow. Now in this case, I pay no attention to the current. But because I'm going opposite the EMF arrow, I wrote a negative E2. Now I'm going to continue clockwise around the left loop. So I go through R1. Now if you look, what current is going through R1? That's not I2. That's only the current in the center little branch. It's I1 in that entire branch. Now I'm going in the direction that I chose for the current. So when they match, it's a voltage drop of the current times the resistance. That's I1 times R1. Continuing on, I get to the EMF device, and now the direction of my going around this loop does match the EMF arrow, so I put a positive E, and that's E1. And then the last element that I find in that loop is another resistor. Notice I'm still going in the direction of my current I1, so it's a drop of I1 R1 again. Now I'm back to where I started, which means all of my jumps and all of my drops have to have canceled out, resulting in a total change of 0 potential. So there's a second independent equation. Now I'm going to do a similar equation for the right loop. So this is a loop equation. The right loop, I'm still going to start at A. That, again, is sort of an arbitrary choice. I'm going to go clockwise because that's what I have drawn for loop R. And the first thing I encounter is that top resistor, known as R1. Because I'm heading in a direction around my loop that is opposite the direction I chose for I3, then I need to write a plus I3 R1 as my first term. That part's a little off the screen, but I think we're done with that. Now I go through EMF device called number 3. I'm going opposite the direction of the EMF device, so that's a minus E3. Then I go through another resistor in the what we might call the wrong direction, but it is the direction I randomly chose, so that's I3 R1. I continue on. I'm going to go up now through the center branch. I don't get anything on the bottom there. I go past that junction called B. I go through E2 in the direction of the EMF arrow, and then I go through R2 in the same direction I chose for the current. So that is a drop of I2 R2. Now I'm back to where I started, so all my jumps and drops have resulted in a net change of 0. So now the equations that you see on the screen here, those three, one junction and two loop equations, are three independent equations. That means they can't just cancel out when you combine them. Now your method of solving this might be as rudimentary as doing a substitution, which is how I learned to do it when I was in algebra, but we didn't have slick calculators, and I never did have a great instruction in the matrix method. But I think now, especially with the calculators, or just doing a hand matrix work, it's just as easy to try to set this up so that you're ready to do some matrix math. So what I'm going to do is I'm going to just advance the screen here a little bit. We can take a look at the independent equations, and all I'm going to do is reconfigure them so that they are in a form that I can easily set up a matrix, and then I'll leave it to you to figure out how to get your calculator or your brain to do the matrix work. All I need to do is get my variables in the same order in each equation, and I think a logical order here is 1, 2, and then 3. Notice my junction equation is already in that form, so I really don't need to do anything with it. But I'm going to rewrite my two loop equations. So I'll write the left loop equation, and all I need to do is put I1 first, and then I2, and then I3. So notice all the terms that have an I1 in it, I'll underline them in red. That's two negative I1 R1s, and so I'm just going to write it as a single term, negative 2 R1 times I1. I like to have all of my coefficient stuff kind of set off in parentheses. I could write that a little better, and I will. That's a negative 2 R1. And then I look for my R2 term, or my I2 term rather, and I just have one of those. It's a plus R2 I2. I have no terms at all with I3 in it, so I'm just going to put plus 0 I3. It seems silly to have it there, but when you set up a matrix, you're going to need it. And then I still have 0 on the other side.
Well, I have to pause it here and apologize for the math mistake you probably just saw. When I was assembling all the terms, all the I terms on the left side, I forgot to assemble the constant terms, or the non-variable, the E terms, on the right side. I just put 0 in there. So in the equation that I just finished, that second equation, we should have an E2 minus E1 on the right side of that. And that's going to become a part of your matrix as well. And then in the final equation that I'm about to assemble here, we would get an E3 minus E2. So I'm going to put a visual note in here, which you've probably already seen, as well as this sort of inserted correction. A lot of years later, I can't believe that I hadn't noticed this before, that a student hadn't pointed it out. So thank you, Connor, for pointing that out, and here's the fix.
Now I'm going to take my right loop equation and reconfigure it, putting the variables in the same order. Now I have no terms there with I1 in it. So I'll put a 0 I1. I have a single term with I2 in it. And it's behind my box here. There it is, a negative I2 R2. So I'll write negative R2. Maybe put that in parentheses to set it off. And then finally, I look for my I3 terms. I have a couple of them, and they're identical to each other. So I'll say 2 R1s times I3. And I can set all that equal to 0. So with the green equation at the top and the 2 lower ones at the bottom, you're all ready to do your matrix math or your substitution or whatever method you choose. So I think we're going to stop there, and I won't continue anymore with the drudgery of all the mathematics. So have fun with that, and I think you've seen the basics here of most of what's involved in doing the Kirchoffs law kind of problem.